Okay, hello everyone. Good evening. I am Shiv Prakash, Research Scholar, Department of Electrical Engineering, IIT VHU. Let's start the session. Today's topic is the MPPT concept. Which is maximum power point tracking. It means how can exert the maximum power from the solar panel, the solar PV. This is the solar system. Suppose if you directly connect a load like that or not, then what happens? This is the voltage Vt, this is the current of It. It draw the current according to the his resistance and then this voltage, and you know about the characteristic of this one. IVP V solar, this is the maximum current. Then this load is directly connected or not, then or not we mention like that. It will vary up to down depending on the or not value. But if you connect directly to or not, it means it can deliver the same amount of current which one needed to the or not or constant current. It may be here this current, this amount of current, maybe this amount of current, this one amount of current, like that. Here like that. Voltage also, voltage vary according to the current, but you cannot get the maximum power from the PV panel. So load is working, but there is a problem according to the voltage rating. If the voltage rating of the load is the same as the voltage rating of the PV, then you can connect like that only. Neither it will be damaged. Then here you can't be get the maximum power from the PV. Then how you get the maximum power from PV? Then you have to implement another devices between them, load to source. It may be power converters, which one operated from the PV panel according to the PV panel maximum power. You know about a maximum power transfer theorem. At a maximum power transfer, anyone know about the efficiency? What is the efficiency? The maximum power transfer. Anyone can guess the maximum efficiency when you transfer the maximum power. So now what is the efficiency of the system, of the whole system? There will be a 50% of efficiency. Oh, 100%. No, sir. There is a 50% of efficiency when you transfer the maximum power in a circuit. Suppose if you DC supply and our source resistance is there, then there is a load R not RS, this one BS. In this system, if you transfer the maximum power P max, in this point efficiency is only 50%. Why? You can observe here in for maximum power RS R naught is equal to RS. It means RS divided by 2 Power is separated from two part only. Whole power losses is in RS and R naught. Both resistance are same, current will be passing same, then power I square into R, because of R naught is equal to RS, both are same, then same power is losses in the both resistance, then efficiency at the output side, this will be the 50% only. But here I apply the maximum power transfer theorem. The source resistance is not there. How can you say in practical source resistance is not there? In ideal cases, you can say source resistance is 0, but in practical thing, there is not ideal condition. It will be possible, but there is the practical thing. We use the maximum power point tracking in practical PV panel. There is a source resistance also, and load is there. Instead of this, we using a maximum power point tracking also there. Why? Because of the there is a no source supply applied by us. There is a PV power. There is a infinity power. You no need to check the efficiency here because of the we can't supply the power input side. Input side is the free of cost supply. You can take any supply from them. There is a no cost. That's why you use the maximum power. How much you can collect from them. Then you should we want to collect the maximum power from them. That's why you're using a maximum power tracking here. In other thing, you can't be take the maximum power in terms of motor. You know maximum torque where you requirement maximum torque, but maximum power if you transfer there, the maximum torque where the needed of this one, then there also efficiency is very less. To get the maximum power, then what happened? You use the converter, a power converter. Any power converter you can use here. There is a DC voltage of a PV, then you should use the DC power converter. It means DC-DC converter. A basic DC-DC converter, you know about the buck converter, boost converter, and buck boost converter. All of the non-isolated DC-DC converter, which one the step up the voltage and step down the voltage, and buck boost is the doing the both step down and step up. You can use here any converter. Then what is the principle of the maximum power transfer theorem? Is the equal to the RS input resistance, load resistance equal to the source resistance. It will be verified by using a duty cycle of the converter. Okay, go to there for the first question. Same thing, same question. I use it. Which one of the following is the best DC converter for the maximum power point tracking in PV panel? Buck converter, boost converter, buck boost converter, cascade buck converter, back to back converter, buck converter. Then after load side, you use the another buck converter. This application is using where the you need a high gain output like that. If you use the step down more voltage like 500 to 10 volt, 500 to uh, 20 volt like that, then you use the two converter back to back buck converter to step down the more voltage to the less voltage. Because of there is a duty cycle 0 to 1 only in ideal cases, but this is not possible in ideal. You can't be give a 0.1 something or 0.05 duty cycle is very less. That's why there is some restriction. You use 0.2 to 0.8 only. You can't exceed this one. There is a restriction. That's why you use the back to back converter to step down the high voltage to the lower voltage. Okay, first is the boost converter, buck boost converter. Let's see which one is the better. Anyone can guess which one is the best better. First, we try the boost converter. The C option, buck boost converter. Yes, good. Are there. No, the then the boost converters source is there, an inductor, the switches, a diode. This is the circuit diagram of the boost converter. The inductor L, voltage across the inductor is VL, switch Q, the diode D, capacitor C. This will be the output resistance of R naught, the current of IC, VL. You can say this was a V2, this was the V naught, output voltage of the load side, the input voltage. What happens if Q switch is on? If switch is on, then VL equal to Vs at this moment, and when the switch is off, like that, the current is flowing to this like that. Then VL is Vs minus of V naught. This was the on time. This was the off time. All of you know about what is the working of this one, but why you ask something like that? There is the inductor and capacitor, but this is the DC supply. Then how it will work? In a DC, generally a inductor is short circuited and capacitor is open circuit. But here is the DC supply, but is inductor and capacitor both are working. Then it should be verify or should be satisfy some equation, some thing. If that thing is verified, then you can be use the inductor and capacitor or the DC supply. There is the flux balance and charge balance. Flux balance for the inductor. Flux balance, it means how much it will be charged at a charging time. Same thing it will be discharged in the discharging and duty cycle is 0. On time is charge some flux, make a magnet like that, and off time it will be discharged. But the amount of the charging and discharging average of this one will be 0. Charging and discharging should be same. If any one is the lesser, suppose is charging is a more respect to the discharging, then inductor will be saturated. It can't be work. It will be a short circuit. Same thing if discharging flux is more than the charging, then inductor current will be 0. Flux will be 0. Then it should verify to the charge balance. Flux balance in inductor for the inductor, and charge balance is for the capacitor. On time, what is the capacitor current? Capacitor current is B. This is the I naught. Suppose it will be constant voltage and current. Ideal cases, then this will be the minus of I naught. And when switch is off, then IC will be a IL minus of I naught. This current is IL. Then for the flux balance equation, this is also known as the volt second balance equation. VL into dt on time plus voltage in off time, average of this one, it should be 0. It means the average voltage of a inductor is 0. Then it will be work on DC also. If this is not 0, then conductor will not work. Then what is the on time? VL is Vs. TT will be cancelled out, Vs into T. Off time, it will be Vs minus V naught. 1 minus D is equal to 0. Vs into D, multiply of this one, then it will be Vs minus D into Vs minus of V naught, 1 minus D equal to 0. dVs will be cancelled out. V naught 1 minus D is equal to Vs. Then output voltage is Vs divided by F 1 minus D. This is the output voltage. Then output current V naught by R, V naught by R naught. Output current. The input current, in ideal cases, we will take an ideal cases for a V naught, I naught, same thing is equal to, this is the input current as a Vs, and you can take as the Is also, is the same as the IL in this case, Is into Vs. V naught, output current is V naught divided by of R naught. This will be Is, same thing we can say Vs divided by of Rs, total source resistance, equivalent resistance at source side, into Vs. V naught is calculated already, this will be the Vs, it will be square, Vs square divided by of 1 minus D square into 1 by R naught, same thing it will be Vs square divided by of Rs. Then what is the Rs? Bs will be cancelled out. Rs is equal to R naught 1 minus D square. Now you can say R naught is equal to Rs. This is the relation between the output resistance and input resistance. We know about for the maximum power transfer, the output resistance it should be same as the source resistance. Then how would verify, because of the load is constant, if you connect the load to the load side of the converter and input side you don't know about the source resistance of the solar, but you can verify, you can calculate the equivalent resistance by using a Vs divided by Is. Then how you can match this one? You can match from the duty cycle. You can use the duty cycle to match R naught equal to Rs for the maximum power transfer. The duty cycle you can change between 0 to 1 only. Can't be exceed the 1 and below to the 0. Then what happen if you take a D is equal to 0? In this condition, R naught is equal to Rs. Okay. Then 1 by Rs is equal to 1 by R naught. When d is equal to 1, then what happen? R naught will be infinity. Then Rs will be 0. 1 by Rs will be I infinity. Why I am taking I 1 by Rs? I will explain you. This is the voltage. You can take Vs, Is. This is graph of the current. Ramya, please mute yourself, please. This is the maximum power here. Suppose this will be Pmax, Isc, short circuit current, VOC. This is y-axis is Is. That's why I am using 1 by Rs, because of Vs divided by of Is is equal to Rs. But if you taking about the Is divided by Vs is equal to 1 by Rs. That's why I am taking 1 by Rs. It will be from 0 to 1. Sorry, or not to infinity, not 0 to 1. At d is equal to 0, 1 by Rs is equal to R naught, 1 by R naught. 1 by Rs depending on the maximum power transfer. So this is the, suppose this is the load line 1 by Rs, it will be varies from here to here anywhere. Can be varies. It depending on the duty cycle of the converter. This is the input source resistance varies, and it find to load resistance, where is the load resistance is same as the source resistance. That's duty cycle. It will be find from the PMPPT algorithm. From the algorithm, it will be find where is the source resistance equal to load resistance equal to source resistance. It will vary, but how, where to where it vary? It vary from 1 by R naught something, 1 by R naught, and 1 by R naught, 1 by Rs is infinity. Here is the infinity. One by Rs is infinity. It means short circuited. The here this line is 1 by Rs at d is equal to 1. Suppose here some anywhere it will be a maybe, it will be 0 to the Pmax line. This will be or 1 by R naught is equal at d is equal to 0. D2 cycle is equal to 0. That means the maximum power it will be taken from here to here. This is the range, working range of the boost converter. It is not the whole the range. It may be taken as the Pmax also. It may not be taken as the Pmax, depending on the load resistance and duty cycle. If the duty cycle is a maximum 0 here, but the load resistance is here only, like this line only, then what happen? It will not take in the maximum power from the boost converter. Can't be take maximum power from boost converter because of it is not getting the load line or the Pmax line. Then it can't be fine. It is the some restriction or some limitation of the boost converter. The range is the here to here only. Same thing if you do from the buck converter. For the buck converter, I'll give some idea of the buck converter also. The switches is a diode, inductor, capacitor and the load resistance. Same thing, this will voltage V naught, this will be R naught, I naught, IL. You know about the V naught is equal to direct I written dVs, and I naught, same thing, I naught is equal to V naught divided by R naught, and Is is equal to Vs divided by f Rs. Then what happened? Efficiency V naught is equal to I naught Vs Is V naught square divided by f R naught, which will be the Vs divided by f Rs. This will be d square into Vs divided by R naught is equal to Vs square divided by f Rs. In this question you can find the load resistance is equal to Rs into d square. Then in this case, if you take a duty cycle at d is equal to 0, R naught is equal to 0, or R is equal to infinity. At d is equal to 1, it will maximum, R naught is equal to Rs. Yeah, you can say 1 by Rs is equal to 1 by R naught, 1 by Rs is equal to 1 by 0. Sorry. Same thing you can draw here, Is, Vs, power line, R is equal to 0, it means infinite. This is the R is equal to infinite means the open circuit. This will be at d is equal to 0. At d is equal to 1, it may be here. R is equal to R naught. It means duty cycle 0 to 1, it will vary from here to here. This is the Pmax line. If this is the is gone beyond to the Pmax line, then you can get the maximum power from the buck converter. This is the range of the buck converter. Boost converter range is above to Pmax line. This is the buck converter range. What happened in the buck boost converter? Sorry, a buck. First is the buck, after that boost converter. Vs, this will be R naught, output voltage V naught, Sorry, current is flowing like that in this condition. I see here. Current is flow like that. When switch is on, current is flow like that. VL is equal to VS, and when switch is off, then current is flowing like that. VL is equal to minus of V naught, because the plus is connected to minus, minus connected to the plus. To draw this one, then dVs or volt second balance equation, flux balance equation, V naught is equal to dVs divided by f 1 minus d. This is the output voltage equation of buck boost converter. And you know about I naught. I naught simply V naught by R naught, and Is simple Vs divided by Rs. Then for the same thing, take the input power is equal to output power. In ideal cases, V naught square of R naught, this is the Vs square bar Rs. V naught is equal to D square V naught square, sorry, Vs square dVs divided by 1 minus d, 1 minus d square into R naught. Oops. So now ask some question. What is this? Buck boost converter should be negative, but your equation so positive. Which one is true? Where is the positive? Okay. Wait. No, there's some, maybe some mistake. It will be negative. Okay, negative shows if you take a reference this one. I will take it as a reference of this one is positive, this one negative. That's why there is a positive in equation, output voltage equation. If you taken a reference here is a negative, same thing like a buck and boost converter. This is the positive, this is the negative reference. In that case, you will get the negative voltage. V naught is equal to minus of Vs, dVs divided by 1 minus d. Because of this only, I have already taken a negative reference of this one. This is negative, this was positive. That's why my equation is the positive in this question. And the question is mentioning you already circuit diagram. The circuit diagram is not given, then you can take a negative voltage, no problem. But in question, it will mentioning the circuit diagram. With respect to the circuit diagram, you can get the output voltage equation. Here, if the reference is here, this is the positive, this is the negative, then you can get the positive voltage equation of the. Don't confuse of this one. It is depending on the reference only. Here is the Rs is equal to 1 minus d divided by of d square into of R naught. Same thing at d is equal to 0, Rs will be infinity, at D is equal to 1, Rs will be 0. It means this will varies from 0 to infinity. Source resistance is 0, it means short circuit. This will be the short circuit at D is equal to 1, R is equal to 0. In this point, at D is equal to 0, Rs will be infinity, it means open circuit. This is the, if you taken a load line on by Rs, according to do this, you can say it will be varies from here to here. D is equal to 0 to 1. We will take in the whole is the operating area for the buck boost converter. That's why the buck boost converter is better for all converter, all basic converter like buck converter and boost converter, because of it will take in the whole area, operating area from D is equal to 0 to D is equal to 1. But in buck converter you take in as the below side only, and boost converter it will take in open upper side only, operating area for the maximum power tracking. That's why for the maximum power it will vary from 0 to 1. It will convert take the whole of the area. This one. That's why this is the better for the MPPT, maximum power tracking. Question number second is asking about the why input capacitance is mandatory at the PV panel output for the maximum power point tracking with the buck converter. You know about the buck converter circuit? Switch is here and diode is here, like that. When switch is on, current is flow on time. Suppose it will be off time. This is the on. Suppose this is IL. This is the IS, source current. Switch is on, then current will be flow like that. IL is connected to the source Vs. That's when the IL current will increases. Same thing, source current is here, same as the IL, the source current also. But when switch is off, then what happened? Circuit will be disconnected from source, and inductor current is flowing like that. Inductor will be decreasing in this area, but source current will be 0 in this moment. This is the source current waveform, and the source current will be discontinuous. That's why a capacitor is needed in terminal of the PV panel, because of the discontinuous current is flowing through the panel. The panel may be get damaged, or this life is reduced in discontinuous conduction mode. That's why a capacitor is mandatory in this condition. A capacitor is added input side of this one. Then the ripple of the input current will be absorbed from the capacitor. That's why this current will be a continuous. Here is this continuous current, but this continuous current is will be continuous. Charge here to here like that. This will protect the solar PV. Now, this option is the input current of the buck converter discontinuous. Next question is given as a 45 watt DC-DC converter shown below. This is the boost converter. Has the following parameter. The switch Q has a saturation voltage of 0.2 volt. This is 0.2 volt voltage drop and switch is on, and the forward voltage of the diode is 0.7 volt. This is a voltage drop of 0.7 volt. What is the input current in amperes? Input current same as the IL. Amperes of the converter for duty cycle of 0.4 under the continuous conduction mode. Okay, first take is the 0 to dt on time. Duty cycle time period of the frequency. Switch is on, that means this current is flowing like that, and the circuit will looks like a inductor, and inductor. After that, this will be a voltage drop. Switch is on, then saturation current is 0.2 volt, then this will voltage also included here. This is 0.2 volt. I retain a voltage drop VQ for this. So voltage Vs, and calculate the VL Vs minus of VQ. Same time, switch is on, then diode will be a reverse bias. Because of the boost converter, this voltage is higher than this voltage. If switch is on, this voltage is higher than this voltage, this and this. That's why the diode will be a turn off in this moment. Then this will be a discontinuous in this condition. Only a capacitor current and a resistor is here or not. So V naught current is IC, I naught. And what is the current of capacitor current? IC is negative of the I naught, and I naught will be minus of V naught by R naught. This will be happen when switch is on, current flow like that in a steady state. Off time, off time circuit looks like that. This switch is off, then this diode will be forward bias, and but there is some voltage drop known as VD, diode voltage drop. But there is a capacitor, there is a load resistance, current of IC, this will be V naught, this will be R naught, I naught. Then at this time, what is the VL? Inductor current, Vs minus of Vt minus of V naught. I take it as the KVL for this. IC will be a, this current is IL minus of I naught will be V naught by R naught. To calculate the output voltage, use the volt second balance equation. On time VL into dt plus on off time inductor current 1 minus dt. Average voltage of the inductor will be 0. Then on time voltage is Vs minus a Vq into D. Tt will be cancelled out. Off time VL is will be Vs minus a Vt minus a V naught into 1 minus D. Tt will be cancelled out. To multiply by this one will Vs dVs minus of dVq plus Vs minus Vt minus of V naught. We can take this as 1 minus D also, minus of dVs plus dVt is equal to 0. dVs and dVs will be cancelled out. This will be the minus of V naught into 1 minus D. This is plus Vs minus of dVq, and this will be dVd and Vd. To take a minus of this one, this will be 1 minus D into Vd, 0. We take a minus a common, then positive, this will be negative, this will positive, this will positive. The Vs will be transferred to the right side. Then we will get the V naught is equal to 1 minus D is equal to Vs minus of dVq minus of 1 minus D into Vt. Then V naught is equal to Vs minus of dVq minus of 1 minus D into Vt divided by f 1 minus D. Output voltage of this converter. This is the input voltage given, then you can calculate the output voltage here. All the drop is given, Vq and Vt due to cycle is all of thing is there. Then you can calculate the output voltage. Then after is asking about the input current. Input current is same as the IL. Then use the currents volt second for inductor. Then use the current second for the input voltage mentioned here 40. Oh, this is the okay, no problem. This is the what is mentioned. Then we can calculate the I naught square odd is equal to 45. You can calculate here. What is given? Then you can calculate the current. After the current, yeah, you can calculate the voltage also by using a equation. The 10 ohm is given. Then you can calculate the I naught. I naught will be a root of 45 divided by of 10. I naught is there. Then we can calculate the V naught also. We can V naught square divided by V naught calculate here from here. But this is the voltage equation or this converter. If this type of converter is given in any question like voltage drop at diode and switches, then you can calculate the output voltage from this equation or the boost converter. From charge balance equation, then IC dt plus IC 1 minus dt, average current of inductor capacitor current will be 0. This is the charge balance I into T. First time IC when switch is on, it will be a minus V naught divided by a R naught, I naught current. When switch is off, this will be IL minus of V naught, 1 minus D is equal to 0. Here, if output voltage is fine, you can calculate, then you can get the IL directly here. If you take V naught by I naught as the I naught, then you calculate that this will be easily also. Like that, if I have taken this will be I naught into D plus this will be IL minus of I naught into 1 minus D is equal to 0. And if you open this bracket, IL 1 minus D minus of I naught plus D into I naught is equal to 0. This will be a cancel out. IL will be I naught divided by 1 minus D. Then I naught is equal to what is given 45 divided by R naught is 10. Then this will be, I think, can calculate from calculator. 45 divided by 10, root of this one 2.12, and due to cycle also mentioned 0.4 in the question. Then what is the IL? So 2.12 divided by 1 minus D, it will be 0.6. Then IL will be 3.53, 5 amperes. You can calculate from here, but for the voltage, if you want to get the voltage, then you can calculate this one. If IL is fine, then you can multiply by this one to the, you can find this one input voltage from this one. Next question, same thing related to this question. What is the load resistance in ohms seen by the PV panel in this question? Then how will get this one? What is the load resistance in ohms seen by the PV panel? PV panel is here. In place of here, this is the PV panel. Then what is this load resistance of PV panel? Is input voltage divided by input current. This is the resistance of RS, same thing. Same converter is in place of DC voltage converter connected through the solar panel. And if you want to calculate the solar output resistance for the solar, this will be the output resistance Vs into Is. Then how to find the Vs? First calculate the output voltage. Output voltage is I naught into R naught. Already calculated, this will then 21.21 volt. I naught will be 2.12. R naught is 10, then 21. 0.2 output voltage. Then from this equation you can calculate the input voltage Vs. Vs, what is the Vs? V naught into 1 minus d plus dVq plus 1 minus d Vq Vd. We are going to calculate V naught is 21.1, 20.2, Vq is given 0.2, Vd is given 0.7, d is equal 0.4. Then we calculate the input voltage also. This will be 13.22 volt. And what is the input resistance? Is same as the load resistance for the PV panels. You mention load resistance for the PV panel, not a load resistance for the converter. Load resistance for the PV panel is the input resistance of the converter. IS same as the IL because of the is the boost converter. Same as the IS 3.535. Three point 739 ohms. Okay, 3.74 ohms. Next question is given, what is the efficiency of the converter? The same question, efficiency. You know about efficiency, V naught I naught divided by of Vs Is. V naught output power is given 45 watt. Input voltage is given, we have calculated input voltage. It will be 13.226 into input current. I already calculated 3.74. This will be input resistance, not input current. Input current is this one, 3.535. 45 divided by 13.226 into 3.535. So 0.9624. If you want in percentage of efficiency, this will be 96.24%. Okay. For this question, first you asking in the first question asking about the input current. For the input current, find the input current. You use the whole current second balance equation for this converter. Then you should know about the how you draw the volt second equation and current second equation. For the volt second equation, you take a voltage of the inductor. For the current second equation, same in the same process, taking the current of the capacitor, because there is a two storing element devices. Storing element is two, capacitor and inductor. These two as varies. What happened? This is not varies. Same thing. Suppose it is a constant current, not ripple. Then what happened? This will be a saturation of a inductor. The inductor will not work for DC. There is some ripple also. Okay, what is the input impedance seen by the ideal boost converter? Same thing I think I will draw in previous questions. For the boost converter, output same. If you ideal converter, use power equation. Input power is equal to output power. Output power is equal to input power. This will output divided by a R naught, the Vs divided by a source resistance, Rs. Output voltage in boost converter is a Vs divided by a 1 minus D. Then there is 1 minus D of square into R naught. Vs will be cancelled out. Then what is the Rs? Source resistance is R naught into 1 minus a D square. I think first question. Which of the following converter has a continuous input current? Buck converter, boost converter, and inverted output buck boost converter, and cascade buck converter. Which one has the continuous input current? For the buck converter, you know there is a switches and this is the diode. Switches here, the switch is on, then the continuous current, input current is flowing. If a switch is off, then current will not flowing through the input voltage. That's why this will be a continuous current buck converter. What about the boost converter? This will be a diode. V naught, Vs. What happens here? If switch is on, then current is flowing through this one. When switch is off, sorry, if switch is on, current is flowing like that. If switch is off, then current is flowing like that. In the both condition, input current will be continuous. That's why boost converter have a continuous input current. Inverted output buck boost converter. Inverted output buck boost converter is same as the buck boost converter. There is a switches, buck, then the inductor. If you taken as this was the V naught reference, then we will get the V naught is equal to minus of Vs dVs divided by f 1 minus D. This is the inverter. This all circuit is the inverted buck boost converter, because of there is a negative input of in output voltage. But simple buck boost converter, if you want to non-inverted output voltage, buck boost converter, there is some other converter known as the Chuk converter, Sepik converter, and flyback converter also is there. Which one is the has no inverted output? There is the simply output voltage is the positive in this that converter. And that converter is known as the non-inverted output buck boost converter also. Both output is the same equation, only negative point is not there. This is the dps divided by f 1 minus d. In this will be the Chuk converter, Sepik converter. If you know about the Sepik converter, flyback converter, this type of converter have a no negative point. Yes, someone is asking something. The input voltage. Yeah, how inverter buck boost converter differ from the buck boost converter? Is the same as the non-inverted buck boost converter is the different converter known as the Chuk converter, Sepik converter, flyback converter, where is no negative in output voltage. And the second, so I mentioned calculated voltage in buck boost converter is positive or negative in This question appear in assignment. Should I mention calculated voltage in buck? If there is a no circuit, then you use the negative voltage also. V naught is equal to minus of dVs divided by f 1 minus d. This is the actual voltage of a buck boost converter, negative. If the circuit is not given, if circuit is given, then according to this or this that reference, you take the output voltage equation. The next question is given: what is the relation between the input voltage V in and output voltage V naught in buck converter when the load is open circuited? Okay, anyone can guess this one? The buck converter, capacitor. This is the open circuit. What happened if open circuit and you use the duty cycle? This is the duty cycle. Then what is the output voltage here? Anyone can guess this one? Try to guess. If you want to calculate this one, what is the actual output voltage? Then first try to do this circuit. This is the if in on time what happened? This is the LC circuit. Suppose t is equal to at t equal to 0, it will be continuous. Then what is the current equation in this? If you know this one, then you can find the what is the actual output voltage of a buck converter when there is a no load. Just trying to find. This circuit will work. A DC voltage connected to the inductor and capacitor. Can anyone guess this one? It will work or not? Suppose it will be ideal cases. Let's do this one and see what happened when in LC circuit when voltage supply is connected and pure inductor and connector. Yeah, someone second is no. Why? Why this will be not working? I am taking because of inductor will short circuited and capacitor will open circuited. Let's take draw mathematical equation, then find what is the current, actual current. Then what happens is this one. If you want to take a KVL, simple KVL, then what is the Vs is equal to VL plus VC. VL you know about this one, L di by dt, and VC 1 by C integration of I into dt. Convert this one in Laplace. Then what happens? This is the constant S by S, L into S Laplace into Is. Current will be go in IT will be Is, time domain in frequency domain. 1 by C integration will be 1 by C S for differentiation d by dt. It will be go in Laplace domain is S, for the integration of something going to 1 by S. Integration, we know about the integral, PI controller, operational integral, gain is same thing, transfer function is 1 by S because of integration. Then Bs by S, if you take an Is is common and Cs is LCM, then LC into S square plus 1, SS will be cancelled out. Then what is the Is? Is is Bs into C divided by F LC into S square plus 1. Sorry. Take LC is common. Bs into C divided by F LC. Then what happen? 1 divided by F S square 1 by LC. We want to convert this one in again in time domain. Then what happened? Taking the inverse Laplace of this one, Cc will be cancelled out. Bs divided by F L 1 divided by S square plus 1 by, can we retain this one? 1 by root of LC square. No, Laplace of sine 80 sine omega t, it will be omega divided by S square plus omega square. This may be omega, if you taken this one S square plus 1 by under root LC is omega. You take omega is equal to 1 by root of LC. Then what happened? This is omega, then multiply this they also needed of omega, then multiply of omega here and omega here also. Is is equal to Vs divided by L, omega is 1 by f root of LC. So this is omega divided by S square plus omega square. For the L, you can written like L into L L into root of C. What is this one? If you convert this one in time domain, same thing, reverse of this one will be a sine omega t. Root of L cancelled out, C will be going to the top of this one, Vs root of C by L. sine of omega t. We take a Vm as Vs divided by C by L, then we can retain this one. This equation is Vm sine of omega t. Oof. You can see here what is the current if you take given to a DC circuit, pure DC circuit, with a LC network providing some switching. Then what happened? Current will be in AC, sine wave. Sine wave will be AC wave. In DC circuit, current will be AC, and the inductor and capacitor is there. This is the, you can say, because of the switching. That's why inductor and capacitor will work here in DC circuit also, because of the switching. You know about the transformer. Transformer is not working in DC, but in isolated converter like flyweight converter, forward converter, push pull converter, this is many type of isolated converter where you use the transformer. There is some switching because of the switching. So you need only two things, or only one thing for the inductor as a volt second valence. It will be balance like a flux balance. It should flux balance in case of inductor. In case of capacitor, it would be charge balance. Is there? Then you can use the in DC also. For this question, current will be Vm sin omega t. Then what happen if you apply this one? Here, suppose this one on time, this is off time, switch off time. This is the inductor current, this is the inductor voltage, the capacitor voltage Vc. Suppose this is the IT, so what is the inductor current? Inductor voltage VL. VL is, you know, L di by dt, simple. If you differentiate this one, Vm is Vs under root C by L. What is the differentiation of sine? Is cosine cos of omega t into omega, because of you differentiate this one with respect to the time. This will omega will be 1 by root of LC. CC will be cancelled out. This will be a Vs by L cos omega t. There is L also here, L di by dt. Then L also cancel out. Then simple Vs cos omega t is the input inductor current. Then what is the voltage of capacitor Vc? Vc is, you can say, Vs minus of VL in this circuit. Vc, what is the Vc? Vs minus of VL. Then Vs is Vs, VL is Vs cos omega t. If you take a Vs common, then 1 minus cos of omega t. Now, someone asking something. The one switching of L and C produce sine wave, but in flyback and forward converter, Secondary waveform is pulse. How? It will because of the switching. If the switching is in a high frequency rate, that's why there is not you can take in as the you can see you can't see the sine wave there because of the high frequency. If you take a very low frequency, then you can get the sinusoidal also. Yeah, this will be because of the in ideal cases, and there is the Vs. We will take in the ideal cases Vs constant like Vs divided by L into dt for the inductor current, where into T, where T is the T on. That's why it will taken like a where T is there. This is the linear equation. In ideal case, it will be taken like a linear there because of the high frequency rate. In high frequency rate, you can take this as a linear sinusoidal. After that, it will be a pulses because of the this will the voltage is there. Voltage will be a positive and negative. There is not a voltage mentioning, but if inductor have some voltage, the voltage will be in pulses like that. If you take a same converter on time and off time, if inductor is like that, the voltage of this one is in positive wave, that the conductor will be charged here Vs supply. When this is the in negative voltage, this is a plus something, Vs is will be a minus of V naught, I think in buck boost converter. In buck I think this, yeah, so minus of this one. If you take a boost converter, buck converter, if you take in a buck converter, it will be Vs minus of V naught, it will be a minus of V naught. That's why it will be pulses of the voltage, but current will be like that. If you taken as the high frequency rate, here in buck converter, what happen if a switch is on, then current is flowing through the L and C. Current is flow in sinusoidal wave, then inductor current will be increased like that, but a voltage will be in a voltage is a cosine wave of a inductor, that it means this will be discharging at this time. After that, this will go to the negative cos. Same time, what happened in BC? BC is 1 minus cos omega t, 1 minus of VL, can take Vs minus of VL, and that time this will be a charging. But suppose it will be charged to Vs, then what happened? If you charge to Vs, then this voltage, if you charge to Vs, then this voltage will be a same. Then after this will be a, after that this will be a discontinuous, you can say this will be disconnected or in open circuited because of this capacitor has a full voltage. After that it can't be taken any current, the inductor current, it will be a zero. After that it will be a maintained continuously like that. The voltage will be a continuous of voltage, you can't be charged more here. That's why capacitor will be a Vs supply if the output is not there. because this, if this will be a disconnected because of this voltage will be same. Both the inductor and capacitor both are charging. This is the Vs, first option. Which of the following is isolated converter? uh, Buck converter, boost converter, and buck boost converter is the basic converter. But flyback, forward, half bridge, push pull, full bridge, all of the use the transformer is there. If a transformer is there, then this will be a isolated converter. In this question, because of the option is given both, then this will be a cancel out, this will be a cancel out, this will be a cancel out, then this will be okay. Because of buck push converter also mentioned in this options. But for a flyback converter, forward converter, half bridge converter, full bridge converter, push pull converter, all of the isolated converters. The next question: a 250 watts buck converter is designed for a PV panel which has the following parameters. Okay, PV panel parameter is given. What is the duty ratio in the range of 0 to 1 required for maximum power point tracking? If the converter is connected to load or not is 0.5 ohm. Consider the ideal condition and assuming the continuous conduction mode of operation. Or not is given 0.5 ohm and power is also given P naught to 50 watts. From here is maximum power is given. Peak power is same as the maximum power. P max is given to 50 watts to 225, sorry, 225 watts. VM is given 29.52 volt. IM is given 7.63 ampere. Then at maximum power point, P max input resistance is same as the input current of the converter, input current or input voltage of the converter is the same as the Vm divided by FIM for P maximum 29.52 divided by F 7.63. This will be 3.869868. This will be 87 ohm. Or not, or not will be V naught divided by I naught. Consider ideal condition is there, then simply use V naught I naught divided by a Vs and into Vs into Is, V naught divided by of R naught, Vs square divided by of Rs, d Vs square for the output voltage, Vs square divided by of on Rs, so you cancel out. what is the D? Sorry, D square also here because of the V naught is equal to dVs. The D is equal to T square is equal to R naught divided by of Rs. Rs same is the R input. Then what is the D duty cycle? Root of R naught divided by of Rs. Load resistance is given 0.5 ohm, 0.5 divided by Rs, calculated 3.87. Can calculate here. 0.5 divided by of 3.87, root of this one 0.359 is the duty cycle for getting the maximum power from the solar panel. The data sheet specification of a solar panel is given below, as the VOC is 43.6 volt, ISC is 5.45 ampere, and maximum voltage at the maximum power point is 35.4 volt, and current at the maximum power point is the 4.94 ampere. Then what should be the load resistance connected so that the load drawn from the maximum power from the solar panel? But taken this one same as R output is same as the R in. R in is the VMP, maximum power, maximum current, 35.4, 4.94. It will be a 1035.4 divided by a 4.94, 7.16. Yeah. Someone is asking some question. What is that? So far you are discussing CCM, not DCM. Does it mean solar PV should operate in continuous and not in this one? No, no. You can operate in both condition. It depending on the inductor current. If inductor current is in discontinuous condition, then it will be a discontinuous. In terms of buck converter is the also discontinuous conduction for the input side, but it's depending on the inductor current. If inductor current is continuous, then you can say this one converter will be continuous conduction mode. Here is mentioning continuous conduction mode in this question because of the output voltage differ in discontinuous conduction. This way formula is not apply. We talk about the buck converter, V naught is equal to dVs. In discontinuous conduction mode, this in the formula is not applied. That's why it is a continuously mentioning about the continuous conduction mode of operation for the converter only. Not for buck converter, if you draw formula, this will be a Vs divided by a beta. Some beta it will be greater than the duty cycle and less than 1 between them. Then you can say in this continuous conduction mode, output voltage is more than the continuous conduction mode for the buck converter, any converter. Output voltage more. For the boost converter, this will be a boost converter. Output voltage divided by of beta minus t in place of 1. This is beta for the boost converter. For the buck boost converter, in place of beta, it will be I think beta d beta b not divided by the beta minus d. This is also more than the in continuous conduction mode. But there is a ripple current is very high in this continuous conduction mode. The ripple current is very high. That means the in term of if you talk about the input side, if battery, suppose if there is some battery, the battery have a ripple current outgoing from the battery, then battery will be lifetime will be deteriorated. That's why maximum time it will be working in continuous conduction mode only. But for some purpose where you need for high voltage and efficiency, in discontinuous conduction mode, the switching losses will reduce. If you read this one in the book, then you can find how you reduce the switching losses because of the current will be zero. Then switching loss, actually switching loss is V into I into T on or T off time into F frequency. But in discontinuous current will be zero. That's why switching loss will be reduced as condition. The power efficiency will improve in some condition, but you need a high rating of inductor also there. Then there are a lot of disadvantage, but voltage will be increased. 11 question is completed. Next is a resistance of 10 ohm needs to be connected to a PV panel. Panel specification is given. Output voltage open circuit 43.6. Sorry, I think same thing in previous question. Same data. In order to extract the maximum power, a boost converter is connected in between load resistance and panel. Okay, the duty cycle at which the boost converter should be operate in order to extract the maximum power. H. It required a 10 ohm of a, can say this is the load resistance of 10 ohm for the PV panel. If there is a or not, if it's 10 ohm, and we use a buck converter, a boost converter, and input resistance, you can find the input resistance of boost converter is the uh, output resistance of the, yeah, solar PV is I VMP divided by IMP. You already calculated this was 7.16 ohm. In boost converter, you know R in is or not 1 minus d square. Same thing from power equation. You can get this one. Then 1 minus d is equal to square root of Rn divided by a or not. Duty cycle is 1 minus root of Rn divided by a or not. There is some glitches in my apps. Sorry for disturbance. Just wait some few seconds. I will connect again. Okay, so for disturbance, this will I in divided by a or not. Or not is given 10 ohm, or in 7.16. 7.16 divided by of 10 root of this one, 1 minus this one, 0.1538 duty cycle of this converter is required. There is a converter. PV panel is given with the maximum power point. Yeah, this is the curve. IV curve is given. Correspond below. Then with the switches S1 and S2 at throw 1 for a duration of DTS, and at throw 2 this is the on time and off time mentioned here, is used for impedance matching for PV to load. Then the operating region will be. And what is the operating region of this converter? For in calculating and determine the operating region for any converter on maximum power point tracking, same thing, you use the output resistance and input resistance and match by the duty cycle. Then first find the relation between the input and output resistance with the help of duty cycle. First suppose it turn on 0 to dt time, you can say this will be on time. What is the circuit of there? One is connected here like that. This is the circuit. I draw a circuit here. This inductor is connected, then this will be sorted through the ground. Another thing is this circuit only. This will be a out. C, this will be I naught, IC, inductor current of IL, VS. Then what is the VL? When switch is on, then VL is same as the VS. Okay. Then what happen if switch is off? This means dt 2t times, means off time. Off time same PV panel is here. For second time, this connected to here, this will connect to here, this will be out from the circuit and complete a circuit from this. In this condition, what is the VL? VL will be a minus of V naught. Apply Bolt second balance equation. VL into D plus 1 minus D VL is equal to D 0. So will be T will be cancel out this. This is a dVs minus of 1 minus D V naught is equal to 0. We can say this is the non-inverted buck boost converter type. Will be dVs divided by f 1 minus D. This is the equation, same thing, buck boost converter, but this is not negative. Same thing, use the output volt power balance Vs Is V naught square divided by f R naught Vs square divided by f Rs. V output is D square divided by f 1 minus D square into Vs square divided by f Rs. Oh, sorry, R naught. Vs will be cancelled out. Calculate Rs here. Then it will be R naught into 1 minus D divided by D whole square. Same thing at D is equal to 0. Rs will be infinity, and at D is equal to 1, Rs will be 0. Infinity is 0, it means short circuit to open circuit. Vs Is current is here, power like that. This is at D is equal to 0. Rs is equal to infinity, it means open circuit. This was at D is equal to 1, Rs is equal to 0, it means short circuit. This will short circuit current. This will open circuit voltage. It means this will be a whole area. This one load line. We will be taking the whole area is the operating zone for this converter. We also know a buck boost converter have whole the area for the Pmax calculation. It means this is the sector 1 and 2 both is the operating area. For the system shown below, if VPV IPV greater than the RL, this input, that means a converter input resistance. You can say VPV divided by a IPV, it will greater than the RL. Okay, then then for the tracking maximum power, interfacing DCC converter should be, it will buck converter, boost converter, a buck boost converter. Yeah, we can use a buck and buck boost both, or you can use buck boost or boost both. RL is output voltage, oh sorry, output resistance. VPV IPV, you can say this is the RS. RS is greater than RL. You can say this is VPV divided by IPV, it will be greater than the V output divided by of I output. If taking a power for the ideal cases, V output I output is equal to VPB IPP in this case. What is the I output? You can say this will be a VPB IPB divided by V naught. Apply here VPB divided by IPV will be greater than V naught divided by VPB into IPV. V naught it will go to top. IPP will be cancelled out, and VP is given here. VPB square is greater than V naught square. It means VPV is greater than the V naught. In which condition? It means step down. Is step down is buck converter or buck boost converter. Both you can use buck boost or buck converter. Okay. The following circuit is used to test the maximum power point algorithm. Then at the maximum power point, the voltage at the load will be. What is the voltage at the load side? You know, for the maximum power tracking, power theorem, or load is equal to RS. There will be half and voltage also half. You know voltage divider. Simply apply a voltage divider. VL is equal to total voltage Vs into which one you want to calculate, where the resistance RL divided by total series resistance RS plus RL. Vs into RL. RL is same as the RS at a maximum power point. RS plus RS is 2 RS. Vs by 2 is equal to 0.5 Vs. Yeah. In order to transfer the maximum power to the load, then value of RS should be. Yeah. This is simple. Anyone can guess what is the RS or the maximum power? B is the R load. R load, okay. Oh, wait. Just once again, read the question once again. In order to transfer the maximum power to the load, it means we want to take a maximum power here. VL you can take. The value of RS, you are asking about this resistance, not this resistance. Then what happened? Okay, let's take some example. Suppose this will be 10 volt. This take as a 1. Then the others, if you want to take a same as for Pmax, RL is equal to RS. So taking this one also here, then what is the voltage here? Adha 5 volt, VL is equal to 5 volt, then PL is equal to VL square divided by f R is 125 watt. Suppose I want to reduce this one 0, then what happen? Because I am asking this one na. If this is the 0, then total voltage appears onto the load. Then VL is equal to 10 volt. Then PL is equal to VL square divided by f RL. VL is equal to 10 square divided by 1 is equal to 100 watt. Okay. Then what happened? In power maximum, RL is equal to RS, not RS is equal to RL. It's not equal to this one. Always see the what is if the load is variable. Suppose if a load is variable, then the load resistance should be a source resistance for P maximum. But if the load is constant, source's resistance is variable, then take a as minimum as possible. If 0, then it's fine. You take the maximum power from them. If there is some resistance, then there is some losses. Like that. If this is the variable, then simply take 0 if it is possible. If it is not possible, then take as minimum as possible. Then 0 ohm is a correct answer here. Okay. Okay, everyone. I want to stop here. Thank you to all. If you have any question, you can ask.